Hello students, today we are going to discuss about the factors affecting the rate of SN2 reaction. In the previous class, we learned the reaction mechanism of SN2 reaction. So these are the key steps, just we recall it. The nucleophile always approach the halogen connected carbon from the back side. This is the first. And the second key step is the nucleophile and the carbon bond formation and the carbon halogen bond breaking happen simultaneously. That means the reaction taking place in single step. The third one, the rate determining step, both the reactants, that is nucleophile and alkyl halide, both are involved in the rate of reaction. Okay, so that's why that is called as bimolecular nucleophilic substitution reaction, in short SN2 reaction, that is kinetic order. Now, what are the factors can influence or affect the rate of SN2 reaction? You see, here whatever we are given nucleophile is in general. R is a general term, X is a general term, everything is a general. Now if we specify or vary the groups or the structures of nucleophile, alkyl and halogen and the nature of solvent, how it will affect the rate of reaction. That only we are going to learn in this class. Now, the first, there are four factors: nature of R, X and nature of nucleophile and solvent. Okay. Now, we go into the nature of alkyl group. Before going into that, let's see some example. Let us take one VIP. He is the VIP, and some terrorists want to attack this VIP. We know this, any terrorist always attack the VIP from backside. Okay. Now this VIP is going alone, walking alone. So then this will be very easy for this terrorist. Okay. It is very easy to attack this VIP. Now, if you imagine this VIP is surrounded by many bodyguards, then what will happen? At the time, if this terrorist is aiming to shoot that VIP, it's very, very difficult. Yes, alright. So, because these bodyguards are hindering, okay, are not allowing to shoot, okay, because they are hindering, create some hindrance. Okay, this is the analogy, the same analogy we are going to see the nature of R group. As we discussed, any nucleophile will approach this halogen connected carbon from the back side. Okay, you know this, the methyl all are hydrogens, the size of the hydrogens are small, so it will not create any steric hindrance. This nucleophile can easily approach this carbon, so the reaction can take place very easily and it may be fast because there is no steric hindrance. Okay, the nucleophile can easily approach this carbon. Now we come to the primary alkyl halide. You see, one of the hydrogen is replaced with methyl. So the halogen connected carbon is alpha carbon. This is called as alpha carbon. There is a branching. Okay, this hydrogen is replaced with this methyl. When you increase the branching at alpha carbon, what will happen? That nucleophile is facing some difficulty because this will create some hindrance. So it will not allow. But somehow this there are two hydrogens, so there is some space is there. So compared to methyl, the primary will go slower. Okay, this will be go slower. But come to the secondary, there are two methyls. Okay, Means there are two branchings at the alpha carbon. Now this methyl will face more hindrance than the primary. So that means this will go fast, this slower, this is slowest. Okay. So this will find very difficulty. This nucleophile is find very difficulty to attack this halogen connected carbon. Now you see in the tertiary one there are 3 methyl groups. That means more branching. So the nucleophile will face severe hindrance. Then it's find very difficult to go SN2 reaction at the tertiary alkyl halide. That means nil or no reaction. Okay. In conclusion, the methyl will go faster than primary, followed by secondary, then tertiary. Okay. This is the nature of alkyl group. Okay. Influences the rate of SN2 reaction. The same analogy for the VIP and the terrace. More crowd, slow reaction. Okay. That's it. So the key points are more branching, reduces the rate of SN2 reaction. Okay. Now see the nature of halogen. In this case, before going to this, let's see some example. Let us take two examples like this. RBr and this is R iodine. If we react with this nucleophile, this RBr will go slow and this will go faster. Why? In this case, iodine containing alkyl halide go faster and bromine goes slower. Why? What is the reason? That depends on the carbon halogen bond strength. Okay. If this carbon halogen bond strength is stronger, then it will go slower reaction. Stronger bond goes slower reaction. Okay. And the weaker bond, faster reaction. Okay. Now, which one decides the stronger and weaker? That can be easily understood from this concept. Let us take this halogen, fluorine, bromine, iodine. Okay. As you know, in the periodic table, if you go down this periodic table, what happens? The atomic radii increases. Okay. If the atomic radii is getting increases, the bond length will get increase. That means the carbon iodine bond will be bigger or lengthier than carbon bromine. Then see, the carbon chlorine is comparatively shorter than bromine. The carbon fluorine is shortest. So that means the carbon fluorine is shortest bond. That's why this is shortest bond. That's why it's a stronger. Okay. The shortest bonds are the stronger bond. That means it requires higher energy. Understood? But the iodine bond is a lengthier bond. Lengthier bonds are a weaker bond that will go faster reaction. Clear? That means in conclusion, the iodine goes faster than bromine, then chlorine, then chlorine. This is the worst living group. Okay, chlorine is the worst living group, and iodine is a good living group. So this is the order. Okay. So the next class we discuss about the nature of nucleophile and nature of the solvent. Thank you.